Hi, myself A. Navin, rule number 49, and my topic is about domain specific languages in scientific computing. Domain specific language introduction. Domain specific languages are special purpose programming languages developed for a specific domain. Some of its most interesting benefits include increasing productivity by reducing the lines of code that have to be written manually, the number of code errors, test generation, formal verification. Domain specific language view types. Domain specific languages work by using higher level constructions and restrictions, which are automatically converted to a lower level programming language at a later time. DSLs can be textual and graphical. Domain specific languages can include multiple views for the same domain. Example, state machine in graphical or XML format. Domain specific languages pre-processing. I've used domain specific languages extensively in my work and it saves a lot of time. I strongly recommend using them. Pre-processing is one of the typical ways to implement domain specific languages. Some subtypes include macro processing, source to source transformation, pipeline, lexical processing. Domain specific languages uses type. You can use this language for many purposes include defining an entity model, example UML, protocol definition, example Google protobuf interface definition, high level user interface description, example Mozilla XUL, automated test case description, software architecture description. Domain specific language development and usage. DSL usage includes two separate stages. DSL development, a new language must be specified. A module to convert from the new language to an existing one must be implemented. The new language should tested and refined. Programming using the new DSL. The new DSL should be imported in the projects that need it. New code can be produced using the domain specific languages. To end the theoretical part of my discussion of domain specific languages, let me add that distinction between domain specific and general purpose is more one of the intended use than of technical characteristics. As an example, consider the text language that many scientists use for writing their publications. Its intended purpose is being a domain specific language for typesetting, but technically it has all the required properties for a general purpose language, in particular Turing completeness. TX can be therefore be used for other applications such as the simulating a Mars rover. Exploring the limits of a language has its merits beyond the intellectual challenge of winning a contest, in particular when it comes to detecting security problems. However, I still consider TX a DSL rather than a general purpose language, in spite of the possibility of using it for Mars rover simulations. In scientific computing, we find two dominant approaches to the human computer interface, not considering graphical users interface because they are used for very different type of interaction. The traditional one is to write application programs usually in a compiled language such as Fortran or C++ that have a broad but fixed functionality. Such programs tend to require a large number of parameters and input files, which they read from a file typically referred to as an input control or configuration file. Since these files are written by humans, their format should be treated as DSLs. A more recent alternative approach is to create a collection of interoperating libraries and let alternative approach is to create a college collection of interoperating libraries and let users write scripts that combine items from these libraries for doing a specific computation. I will try to illustrate these two approaches by a toy example. The computation of the electrostatic potential of a set of point charges. A traditional program would require an input file looking like this. The program user's manual would explain that each line describes one point charge by four floating point numbers separated by spaces. The first three numbers being the Cartesian coordinates in nanometers and the last number being the charge in elementary charge units. Without this explanation, the file would be impossible to interpret for a human reader. Even for a reader who knows that the file describes 4-point charges, it is not obvious if they are stored by line or by column, nor if the charge comes first or last. Next, let's look at a Python script using a hypothetical library called electrostatic potential. From electrostatic potential, import charges system, import numpy as np, and we here see the charges. Energy is equals to charge system of charges dot potential energy. Print the energy is comma energy. So what would a proper DSL for point charging systems look like? A good starting point is to consider how the information would be presented in a scientific article. This table contains exactly the information we wanted to store, neither more nor less. This could be translated straightforwardly into a machine readable file. Here we see the position and charge. To make sure that this table syntax is a valid formal language, I would have to show that it can be parsed unambiguously by a computer program. The proof would consist of actually writing a parser, but I can spare myself that effort because others have already done it. I have borrowed the table syntax from an extension to the lightweight markup language. The main obstacle to human-friendly domain search languages is the effort required to implement them. Computational scientists are not specialists in parser development, so it's not something they are particularly eager to do. There are, however, various libraries and tools called parser generations that make the task easier, but even if you prefer to avoid writing parsers altogether, there are useful compromises that are much easier to implement while retaining many of the advantages of human optimized domain searching languages. The general idea is to pick a syntax for generic data structures and express your domain searching languages in terms of them. You can then use of an off-the-shelf parser for the data structure syntax and do not have to write your own. As a bonus, you may find that the favorite text editor already supports such data structure syntax. That's all about my topic. Thank you.